This is 11.6, absolute convergence and ratio and root tests. So a series summation A sub n is called absolutely convergent if the series of absolute values is convergent. So if I were to take the absolute value of this particular series, okay, of A sub n, and if it's convergent, we call it absolutely convergent. And obviously, if the absolute value is convergent, then that means that the original series is also convergent. Okay, so the whole thing about absolutely just basically means is that I'm applying an absolute value to A sub n. Okay, however, a series summation of A sub n is called conditionally convergent if it is convergent but not absolutely. So for example, if I take the sum of the absolute values and that doesn't converge, but if it converges without the absolute value, we call it conditionally convergent. So let me give you two examples of what one of them is a conditional and which one of them is going to be a regular absolutely. So let me do this quick example. So let's say we have the sum from n goes from 1 to infinity of negative 1 to the power of n over n, okay? Which is kind of something that we've done in the previous video. So we want to show whether this is going to converge absolutely. So one of the things that I'm going to do is I'm going to take the sum from n goes from 1 to infinity, and I'm going to apply absolute value on them, okay? So what I'm going to get, this whole top term is just going to become positive, because if I take the absolute value of a negative thing, it's going to give me positive. So I'm going to get the sum from n goes from 1 to infinity. And then the absolute value of n, well, n is never going to be negative. It starts at 1 and continues. So it's just going to be the sum from n goes from 1 to infinity of 1 over n. Okay? Now this is just a harmonic series. Or you can say a p series with p equaling 1. Now we know that this is going to be divergent. This diverges either by p series or by harmonic series. So you can say whichever you want. But what else do we know? But by alternating series tests, when we just proved this to ourselves in the previous video, this converges. Okay? So thus, this series is conditionally convergent. Okay, which means that the series itself converges, is still converging, but if I were to take absolute value, it's not going to converge anymore. Okay, so now let me give you an example of something that might be absolutely convergent. So let's say you have the sum from n goes from 3 to infinity of negative 1 to the n plus 1, n plus 1 over n cubed plus 1. Okay, so now is this going to converge? Well, let's see. Okay, well, this is going to be n goes from 3 to infinity. Let's take the absolute value of all this thing, n plus 1 over n cubed plus 1. Okay, so this whole thing is going to turn positive. This guy is also going to be positive because it doesn't take any terms that are negative. So I'm just going to have the sum from n equals 3 to infinity of n plus 1 over n cubed plus 1. Okay, so now we have this new series. Okay, now this new series, you can do many different things. Maybe not a test for divergence, maybe not an integral test. I think maybe a limit comparison test. I'm just going to compare this with b sub n. So let's say b sub n is the comparison. So I'm going to compare the leading terms, okay, which is going to give me 1 over n squared. This is a p series, okay, p equals 2, which is greater than 1, and any p series that has greater than 1 is going to converge. So if this converges, by comparison test, this also converges, okay? So we just figured that out. Now, if you don't quite want to do, if that still is not believable to you, you can always just use a limit comparison test. So you can do the limit comparison test. So c is equal to the limit as n goes to infinity of, you're going to take this one n plus 1 over n cubed plus 1, okay, and multiply this by the reciprocal of this, okay, so which is going to be n squared over 1. Oh, this should be multiplication, not absolute value, okay? So we're going to have the limit as n goes to infinity. I'm going to distribute this guy to the top. That's just n cubed plus 1 over n cubed plus 1, okay, which is going to give me 1. Because c is a number that's greater than 0, by the limit comparison test, this converges. Okay, so because the absolute value converges, and initially you can show that by alternating series, this is also going to converge by having this equal b sub n, okay? This series is absolutely convergent. Be wondering what is the whole point of absolute convergence and conditional convergence. It basically just means that if I were to sum, if I were to kind of like write down all the sum of some of these series, and if I were to add up all the values that are absolutely convergent, so for example, this guy, if I were to write out every single term, doesn't matter how I rearrange the terms, you're always going to get that particular sum. However, if something is conditionally convergent, like this guy, I can rearrange the terms any way that I want, and you will might get a different sum. So basically, absolutely convergent is very powerful, means that it doesn't matter, there's one sum that this is going to converge to. However, if it's conditionally convergent, you can rearrange the terms as such, and you might not get that same sum. Okay, so it's really, really important. So now there's another way that we can kind of test this instead of doing all of this work. And this is what we call the ratio test. So the ratio test has three different things. So if the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to some limit that's less than 1, then the series is absolutely convergent, which actually implies that the whole series itself is convergent, okay? If the limit as n goes to infinity of the ratio between a sub n plus 1 over a sub n equals some limit that is greater than 1 or infinity, then the series is divergent, okay? If it equals 1, if this ratio between these two things is equal to 1, then the test is inconclusive. Okay, so the ratio test is a very good test, and we're going to be using the ratio test a lot. So let's go ahead and do a problem with the ratio test. And one of the ways that we kind of want to think of doing the ratio test is that whenever you see kind of like factorials, like if you have like n factorial, which basically means that you're taking n, then n minus 1, then n minus 2, then continuing to subtract a whole bunch of terms until you get to 3 times 2 times 1. Whenever you have terms that look like a factorial, the ratio test is usually a really good test to do series that have factorials in there. So if you have 5 factorial, this just means 5 times 4 times 3 times 2 times 1, just in case you forgot what a factorial was. So let me do one example of this. Okay, so here's an example. So determine if the series is convergent or divergent. Okay, so that's what you want to be able to do. So the sum from n goes from 0 to infinity of n factorial over 5 to the power of n. Okay, so that's what we want to do. Okay, so because this has a factorial, the ratio test might actually be a really good way to do it, okay? You definitely do not want to use the integral test here, and this is not an alternating series. You don't want to quite put it as a p series either. This is definitely not a p series. It looks kind of like geometric, but you have a factorial on the top. Okay, and the comparison test might not be probably the best way to do it. So let's go ahead and use the ratio test. Okay, so I'm going to use ratio test. And basically what the ratio test says is that I need to take the limit, regardless whether it's going to be convergent or divergent or inconclusive, it always is the same. I have to take the ratio between the n plus 1 term divided by the divided by the nth term. So here is going to be my a sub n. Okay, so here a sub n is going to be equal to n factorial over 5 to the n. Okay, so my a sub n plus 1 term is basically plugging in n plus 1 into the n. So we're going to have n plus 1 factorial over 5 to the n plus 1. Okay, and all I'm going to do is just take the ratio of these guys and take the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. So I'm going to have the limit as n goes to infinity, absolute value. So first let's write the n plus 1. So that's going to be this guy, n plus 1 factorial over 5 n plus 1 divided by a sub n, okay? Divided by this guy. Well, one thing that you can do when you divide it, you just are basically flipping the fraction. So it's going to be 5 to the n over n factorial, okay? Okay, now at this point, this I think is what makes it a little bit difficult, because now this whole thing, you have to use algebra, okay? So whether you're good or bad at algebra, you have to be pretty good at it by this point. So you have to be able to be very comfortable with the factorials, and it takes a little bit of time. But let me go ahead and show you what we're going to be doing. So the whole point of this is that you want to be able to cancel as many terms as you can. So the top part, let's leave the factorials by themselves for now. N plus 1 factorial. This guy, we can break it up as 5 to the n times 5 to the first power. That's just a power exponent property. And then a 5 to the n over n factorial. Okay, so the 5 to the n's can go away. So I'm going to be left with the limit as n goes to infinity. So on the top part, we're going to have an n plus 1 factorial divided by a 5 to the first power, which is just 5, times n factorial. Now, what are we going to do with the factorials? Because there's only room for one factorial here. Okay, so what we're going to do, we're going to try to expand it. So kind of how we had it here. So see how we had n factorial, and then basically in order for me to expand n factorial, you just get n minus 1, n minus 2, so on and so forth. Okay, that's what I'm going to do. So I'm going to take n plus 1, and then I'm going to subtract by 1. So that's going to be n. Subtract by 1 again, n minus 1. Subtract by n again, n minus 2. And we keep doing this until we get to 3 times 2 times 1. Okay? Divided by 5. And then I can continue expanding the n factorial. This is going to be n. Then subtract by 1, n minus 1. Then n minus 2. And then continues on until we get to 3, 2, and 1. Okay, now notice that this whole thing is going to cancel out this whole thing. So what I'm left with is the limit as n goes to infinity of the absolute value of n plus 1 over 5. Okay, now because n in this case is just going to be positive, I can drop the absolute values. So we have the limit as n goes to infinity of n plus 1 over 5. When we plug in the infinity, we're just going to get infinity. Infinity is a number that's greater than 1. And when it's greater than 1, what's going to happen? Well, if it's greater than 1, the series is divergent. So by ratio test, the sum from n goes from 0 to infinity of n factorial over 5 to the n diverges. Okay? Okay, now the tricky part was being able to expand this. Now, if I were to kind of look at this one more time, because do I really need to be expanding all of this guy out? No, you don't. You could have just done this. I have the limit as n goes to infinity of absolute value of n plus 1 factorial over 5 n factorial. One thing that you could have also done, and after a while, maybe in the beginning, you might have to do all of this, expand it out and then cancel them out. But after a while, you might do n plus 1 times n factorial divided by 5 n factorial, because n factorial is just going to be subtracting 1 over. Notice that the n factorials cancel out and you're just left with the same thing. So you can save yourself a little bit of space in your paper by just writing it and stopping at n factorial. Now, if you don't feel comfortable with this yet, you can just go ahead and just write everything out and it'll still cancel each other out.